Hello and welcome to Cognitive Psychology, Lesson 1, Human Memory, Short-Term Memory. This is hands down one of my favourite topics, and the reason why is because short-term memory is so indispensable as a human function. Without short-term memory, you can't really experience any continuity of reality. It would be a bit like an animation on a very slow frame rate, and really it's short-term memory that knits every moment together, turning it into what Badley talks about as being a sort of seamless experience. So short-term memory is very important. It's an area you can actually improve yourself on, and we'll talk about that in a couple of lessons' time. And it's vital for holding short amounts or small amounts of information for short periods of time. So let's dive in. Now, cognitive psychology and human memory. Let's have a bit of a recap on this. So you know some of this already. We've always been interested in memory since man started laying down, pictures in caves. It was a way of just recording perhaps perception, what they saw. It could have been expression partly as well, but largely we think that cave paintings and things like that were a form of record. So it was all an interest or a recognition, you could argue, that memory fades. The memory is not permanent. And that may actually be a battle against short-term memory. Today we write things down, we jot them down, we put them in our phones, and all of that is this constant battle with short-term memory. And the ancient Greeks come up with one of the best systems of for remembering things. My personal favourite, which is the method loci, which I use quite frequently. And the key to this method is to actually access your long-term memory directly without having to rely on rehearsal or some other mechanism. It's essentially a hack of your memory system to remember information in a more efficient way, you might say, and bypass short-term memory limitations. Modern memory research sort of emerged from the empiricist philosophy of Hume and Locke, and they were very interested in the nature of mind, or in their case, the brain perhaps. And then we had the more scientific approaches, which you could argue were spurned on by sort of Wundt's methods, laboratory-based experiments, but researchers like Ebbinghaus and Jacobs, and of course the ones we'll come to see, people like George Spelling, Miller, and so forth. Memory research for a while was wrapped up with behaviorism, so in the behaviorist-dominated period of the early part of the century, 21st century, we saw this sort of link between learning and memory. That association has been weakened to an extent. We now see memory as something slightly different from operant classical conditioning, though obviously that is a type of memory of sorts. It's a way of remembering, imprinting on our behavior in some way. And then memory research made its huge leap forward in the 50s and 60s with the advent of the computational paradigm, which we will talk about today, and with key researchers like Alan Badley, people like Atkinson and Shiffrin, people like Barak, and we'll see some of those characters coming out in the next couple of lessons. So, interestingly, going forward, if you're interested in this topic as well, there's a lot of interest in research at the moment about the biological basis of memory. There was this thought that you could sort of find memory engram, this trace in the brain that might be a few neurons or something, and that'd be the physical basis. That's not quite where we're at the moment, but there is a lot about the biological basis of memory and the structures in the brain responsible. We know the hippocampus, for example, is really important for memory. But there are other structures as well involved, and we may talk about those as we go through. So, the cognitive approach. Memory has been dominated by cognitive psychology, and the reason why is because really cognitive psychology is interested in the processes. And memory is a process. It is taking stimuli that we experience through the environment, that we record, and then storing it somehow. Now we know, a little story when I was a child and I watched, TV shows, I didn't quite understand how photons worked. I thought when I was a very young child, I have to stress, that there were little people in the TV. that's a belief that a lot of children may hold, or may take for granted. The reason why is because you try to make sense of the world in any sort of way that you can. Well, what the cognitive paradigm allowed us to do, or the cognitive approach really, is to view the human mind and the memory system and things like that in a much more logical way, and to really find a model for human memory. So remember, the cognitive approach emerged out of dissatisfaction with the behaviorist approach. In other words, a more simple model. And there were lots of things it couldn't explain, really. One of those things was that there seemed to be some activity in the middle. So you had stimulus, something comes in from the environment, you respond to it, but there's something happening in the black box, as it were. And the black box is the brain, we know that. And we know there's a lot of processes. So inferring what those processes were was the key job of cognitive psychologists. They looked at the computer, the development of the brand new computer, which would have been pretty much the size of a house or a building or a very large room, and would have had less processing power than some watches. And yet they looked at it and thought, well, we're putting information into this machine and something's coming out. Now, I've sent you a link to a BBC Bite-size article, as it were, or a little part of the website on IT. Now, you may have forgotten a lot of this from your IT that you studied low down the school, but it's worth recapping a few things, like what is ROM, what is RAM, the basic input-outputs of a computer, and that will give you a slightly stronger understanding of where cognitive psychology is coming from. So we rely on mental processes, just like a computer has processors internally. And we have inputs and we have outputs. Well, psychologists started to develop models of how the mind might work, and specifically how memory might work. These models were then testable. We'd come up with experiments to say, sort of, if the model predicts this, then let's carry out an experiment. And if our findings are consistent with our predictions, and that gives some validity to the model. And we're going to look at two models of memory in a couple of lessons' time. So, remember the assumptions of the cognitive approaches. It's pure science. We're interested in laboratory experiments. Behavior can be explained in terms of processing, operations, how the mind works. And it takes an information processing approach, just like the computer. The mediation processes occurring between stimulus and response. We're interested in memory, but we're also interested in perception and some other cognitive processing, reasoning, morality, all sorts of things like that. And really flexible. The reason why cognitive psychology is still relevant in a way that many past approaches tend not to be is because it's so successfully combined with other disciplines. Neuroscience, as you know, behaviorism in the form of CBT, and many others. We will spend some time looking at these combinations later on in this topic. So, what do you need to know? For this session, I've chopped up the specification in a slightly different way than is laid out here. They normally suggest go straight for the multi-store model of memory. I'm not going to do that. I'm actually going to start with the different systems of memory. So we're going to look at short-term memory, long-term memory, and the sensory registers. And then when we come to the multi-store model, we'll have an understanding of what each of the components are. The reason why I've done this is because they actually reserve the right to ask you a relatively large question on short-term memory in an evaluative sense. So it's worth knowing about STM specifically, and then fitting it into our models as we go through. The other reason is the working memory model is also a model of short-term memory, so we can clump those together. The key things you need to know about today is the coding capacity and duration, which we'll define in a second, and the key research, plus the evaluations of short-term memory. So, these are the key questions I'll be asking you in class. You can answer them now, or you can wait to class and test your memory. It's entirely up to you. Either way, I expect 80% accuracy, so make sure you prepare and read these notes. Write down the guide notes if you want, but I'm not going to spend long on these. These are for class. and the key terms. So coding, or sometimes encoding, what we mean is changing a material from its original form into a different form. The universe is just one big encoding system, really. Everything, matter, gets changed back and forth into different types of materials. The human memory does this as well. So if I go back to my little people in the TV example, if you open up the back of the TV, there's not little people in there. So in other words, what you're seeing is being translated somehow. Now you know that ultimately it's an electromagnetic signal that's being detected in some way. It's probably coming down a fiber optic cable, and that information is being transferred into a picture. You know, cowboys and Indians on the television. There's not actual cowboys and Indians in there. That means it's being changed. It's being encoded from its original material, which would have been people running around dressed as cowboys and Indians, recorded onto a digital camera, transmitted, and then received via your TV set. That's the process of encoding. The final material, the final state of the material is different from the original state. And your memory system encodes things. It can encode things in many different modalities. Modalities are just any way that it can be changed. But the main ones we talk about are visual, semantic, which is all about meaning, acoustic, haptic or tactile, which is about touch, and taste potentially. But in cognitive psychology, we're going to focus on visual, acoustic, and semantic. Capacity literally refers to how much stuff you can fit into a particular location. Any box has a particular capacity, a jug will have a particular capacity. Your memory system has a capacity. Your short-term memory has a very limited capacity. We'll see what that is in a moment. And duration, how long information can stay in the system before you lose it. So, let's start with capacity. Capacity we can measure using a box. So you could conceptualize short-term memory as just being a sort of little box in your head somewhere that you can hold information in. It's a relatively small box. There's not a lot of space in there. Jacobs carried out some early research on this in the 1800s, where he presented participants with increasing lists of numbers. So basically, it starts with a relatively few, a small list of random numbers, and increase that list each time. He defined this as the digit span. And your digit span is the capacity of your short-term memory. And it's measured at the point at which the list increases and you can only remember 50% of it. So that's your digit span. When you reach the point where you can remember 50% of the items, that's your digit span. In his research, he tried numbers and he tried letters, and he found different digit spans. He found that on average, participants had about a digit span of 9.3 for numbers and about 7.3 for letters. There are many reasons why that may be the case. One is, of course, that there are only 10 numbers that you have to remember, 0 to 9, whereas the alphabet consists of double that. So really we're talking about, that could explain the difference here, but the difference isn't really relevant. This number though, 7.3, I want you to remember. He also found that there are age differences, and you may notice that children struggle very much to remember a short list of instructions. By the time you've asked them to do this and that, they've forgotten the this. And you yourself may find it difficult to follow, even though many of you are in the prime of your sort of mental lives, which may be slightly depressing. Anyway, here's an example of a digit span. So on trial 1, we just give the participant 3 numbers in serial order. We might read them out aloud, or we might present them visually. We might say 5, 9, 0, and ask the participant to recall those 3 digits. What Jacobs found, and what many subsequent researchers have found, is that when we get up to about 7 items, 1, 2, 3, 4, 5, 6, 7, it's at that point that we start to decline. So we can only really remember about 7 items. Because when it comes to digits, remember a few more, we refer to this as the magic number 7, plus or minus 2. So you may have a digit span, and we've tested this before, but we'll do it in class again, of 5. That's perfectly normal. Or you might have a digit span of 9. Some exceptional people have been known to have digit spans of 11, 22 I've heard of, but really it's pretty limited on average. It's about 7 plus minus 2. As you can see here, and this concurs with what Jacobs was saying, digit span increases with age, but it plateaus and it reaches a sort of optimum of around 7. Now, if you could only remember 7 items in short-term memory, that would mean that you could not even remember your own phone number, given that it's many numbers greater than 7. You wouldn't be able to remember words, potentially, or how to spell words, if you wouldn't be able to learn them in the first place if they're more than 7 letters. So something fishy is going on here, and Miller was one of the early researchers that investigated the role of chunking. And what these early researchers discovered was that we do not remember single items when presented, for example, with a word list or a list of letters or a digit span task. We actually chunk the information. And you do this every day of your life, and you've been doing it for years. You do it with phone numbers. When you try to remember your phone number, and you may be sitting there thinking, I still don't know my phone number, that's perfectly natural as well. When you first tried to learn your phone number or someone else's phone number, you did it in chunks. 07795. We do that chunking, and that means that we're actually remembering less information. 07795 becomes a single item for memory to remember. So now our 7 plus or minus 2 could consist of 100 items in total. Have a look at this. F, B, I, C, B, S, I, B, random letters. But when we chunk it into something meaningful, FBI, CBS, IBM, IRS, now we've got 4 chunks to remember, not a series of letters that would surpass our capacity. So Miller suggested we chunk each number, and he called it the lifeblood of the thought process. And really, it's an important feature because there's so much you wouldn't be able to do if you were restricted to that 7 plus or minus 2 items. A word with eight letters might be really difficult to remember, but instead you chunk it. You chunk bits. This improves the capacity of short-term memory, expands it effectively, but it's also really useful for processing as well. Finally, coding. How do we actually code information or in short-term memory? Well, we code it acoustically according to Conrad. Now, Conrad used a paradigm which is called substitution error paradigm. And what the substitution error does is that it essentially means that when 2 items interfere with each other, that tells you that may be the modality in which information is being stored. Let me think of an example. So if we have 2 pieces of acoustic information and they get in the way, so let's say it could be 2 words to remember. Map, or 3. Map, mad, and mat. Yeah, map, mad, and mat. Conrad found in his study that you were more likely to make mistakes when information sounded similar than you were if information sounded different. So, map, mad, mat, there were a lot of substitution errors. But when it was dog, hat, and tree, no substitution errors or fewer. So that suggests that information in short-term memory is being coded acoustically. Effectively, we're converting it to whatever original format it was in and then turn it into acoustic. Just have a look at, I'll go back to these numbers. Just remember this number for me. Alright, hold it in your memory. Right, now it's gone. Just think about how you're remembering that number. Chances are you're saying it out loud. Chances are you're saying 315, 964, and so forth. That suggests that we're actually taking that information and we're converting it from a visual stimulus. This is visually presented. I didn't read the words out, the numbers out to you. I asked you to read it yourself. And you're converting it from a visual image to an acoustic sound. And it's that sound that Conrad says is the form in which we encode information in short-term memory. So that's coding. We encode stuff, whether it's visual or touch, wherever it may be, acoustically. And sorry, this is the final one, not Conrad. Duration. Duration is the amount of time we can hold information in short-term memory. Now, it's called short-term memory, so the clue is in the title. So it suggests that we actually can't hold information in there for very long. And that seems to be the case. Peterson used what's now sometimes referred to as the Brown-Peterson technique, where they use nonsense trigrams like BRK. Doesn't mean anything. They might not use that. They might use BKR. So as long as it doesn't resemble a word, it's fine. Nonsense trigrams of letters, 3 letters. And they would present these to participants, and they would give them an interference task where they had to count back from a random number. So it might say count back from the number 389 in threes. So you go 389, 386, 383, all the while trying to remember one of these trigrams, BKR, over and over again. What they found was if you test people, let them do that for 3 seconds, and then ask them to recall, they remember about 80%. 80% after 3 seconds. Here's the graph. But if you wait up to 18 seconds, then actually participants remember around 10%. So they've forgotten 90% of the information that you've given them. It's only a trigram, 3 letters, but they forget 90% of those when given an interference task, if they perform the interference task for 18 seconds. And this said to Peterson that the duration of short-term memory is very limited, around 18 seconds, if rehearsal is prevented. Some subsequent research suggests it may be up to 30 seconds, so a good range between sort of 18 and 30 seconds, but certainly less than a minute. If information that lasts longer than that tends to be held in long-term memory. You see a pretty stark decline over the time. So this suggests that short-term memory is very limited in its duration. Now, where's the information go? Well, it just disappears. Nothing can disappear in the memory system. Effectively, you can think of it as decaying. Imagine an image that's rotting and gradually sort of, or set fire to the middle of an image and it just starts to like spread out and delete everything on there. That's what's happening in short-term memory. It's decaying. Or being displaced. We'll talk about that when we get to forgetting. So, that's the AO1. That's what you need to know about describing short-term memory and the boundaries, the coding, the capacity and duration, but you also need to be able to evaluate. Now, I've given you some sort of half PE points. Some I've filled out for you, some I expect you to fill out yourself. That's what you're going to use the notes section and your guide notes for. Simon in 1974, for example, criticises the idea of chunking, the idea that all chunks are equal. He suggests that the size of the chunk does affect your memory. And he suggests a negative relationship between the size of the chunk and how many chunks you remember. In other words, if one of your chunks is cat and another is dog, that's one thing. But if one of your chunks is anti-disestablishmentarianism and your second chunk is an equally long word which I can't think of, phenylketonuria, for example, those two chunks suddenly are not equal. You're not going to be able to remember as many of those types of chunks, those long chunks, as you are cat, dog, hat, tree. All right? Good. However, a practical application of the idea of chunking is it kind of explains how children develop. Remember when we went back and Jacobs, he found age differences in short-term memory capacity that basically get better with age. Well, his idea could be explained by Case's argument, which is that Your short-term memory capacity is largely fixed. It may have some biological limitation to it, but over time, the reason why it grows, it becomes larger essentially, is not because it physically gets bigger, that you have greater capacity. It's that you use your capacity more efficiently and more effectively. So you just get better at using it. You can imagine someone with a notepad might be able to write out everything that someone is dictating to them. So you're sitting there listening to me in class, and you're writing down everything that you hear me say. However, someone with who could do shorthand, they could write down twice as much. They're using the same amount of space, but they're achieving more. They're recording more. Visual coding and short-term memory. The idea that all information is always coded acoustically, as sort of suggested by Conrad's research, has been criticised. Posner, who is a really important researcher in cognitive psychology, carried out a very nice little experiment in which capitals of letters were presented along with a capital and a lowercase, and he found that there was a difference in reaction time. Now, if you think about it, if you are processing information acoustically in short-term memory, how it's depicted shouldn't matter because it's all converted to the same sound. Or A, sorry, I'm doing phonics for my daughter, but the sound for A is the same whether it's capital or lowercase. It doesn't change. So Posner found that actually there was a difference in reaction time. When they looked the same, reaction time was faster. That suggests that there is some visual processing occurring in short-term memory. Brandemonte supports this and showed that you could still process information visually even when acoustic rehearsal was prevented. And there's a really good link here, synoptic link for a few lessons time, which you can have a look at, which is KF's research on KF case study, where his acoustic processing was damaged but his visual processing remained intact. Final points on evaluation. Cohen suggests that the capacity of short-term memory may be overstated, arguing that we have a much more limited capacity functionally in short-term memory. And the reason why we may see this magic number 7 pop up is possibly because the artificial stimuli that participants often are asked to use in these highly artificial experiments. Remember, if you're using a methodological criticism, you're criticising the research carried out in the field by saying it relies heavily on list learning of nonsense or random words, and this may lack ecological validity in this case. Specifically, how would this explain short-term memory of me forgetting someone's name that I just met? Yes, a random list, I understand that. Highly controlled lab experiments, this is a good thing. You can establish cause and effect very nicely. Another limitation though is the cognitive approach generally relies on inferences, and short-term memory cannot be directly observed. So it's currently not within our power to say, okay, input in, this is what's happening, look, we're observing it right now, and this is what's being output. So there's a lot of inference, and the models tend to be fairly oversimplified, as you will see when we get to the multi-store model in a couple of lessons time. So that has been short-term memory. We've looked at coding capacity and duration, and we've looked at the key research by Jacob, Miller, Conrad, and Peterson. As always, thank you very much for your time, and if you have any questions, you know where I am. Have a wonderful day. I'll see you next time. Bye.